Okay, so welcome to week 5 of Fundamentals of Nano and Quantum Photonics course, which is offered on NPTEL portal by IIT Madras and IIT Hyderabad. And the course instructor is Professor Naresh K. Imani. I'm Shazan Bhatt and I'm a direct PhD student at IIT Bombay and TU Berlin. So today what we are going to see is as we are moving through in this course, we are into week 5 and we are going to study about how the electromagnetic waves behave in a stack. Let's say, for example, you have, let's say, a stack like this of different layers. Then, if a electromagnetic wave comes in, then how is it going to behave? Whether it's going to get reflected or going to get transmitted, or there will be some diffractions or what basically is going to happen to this electromagnetic wave. That is what we are going to happen, and what are the rules governing its propagation, reflection, or transmission inside this particular what we are talking about layered structure. Then we are going to see a very cool trick which is basically called as T matrix in order to analyze what will be the reflection and transmission coefficients. Let's say, for example, you have a structure and it is having different layers. Then T matrix is a, I should say, mathematical approach, a matrix approach where you can basically find the reflection and transmission coefficients, let's say at this point and at this point of the interface. Similarly, here and here, here and here, here and here, so on and so forth. Okay, so if you can relate these particular uh, you can relate these particular dots, just like for example you can relate this the reflection and the transmission amplitude at this particular point. Similarly you can relate these two, similarly you can relate these two, so on and so forth. In a stack, as you go, you will be able to know the reflection transmission of the electromagnetic wave along this particular stack using this T matrix approach. Then we are going to talk about this photonic band gaps, which is almost similar to that of the electronic band gaps, and we are going to see the analogy of the electronic band gap with that of the photonic band gap. Then we will move briefly into the diffraction grating, which is almost similar to producing, I should say, different wavelengths of the electromagnetic wave or frequencies. It's just like dispersing them. Okay, now we are going to go a little bit into the details of it and also see the maths, what are the governing equations. And for some reason, my camera, the Gmeet is not allowing to share the camera and the screen at the same time. So I'm unable to share my camera. So these are the references I have been talking about. There is one more book named as B.S. Saleh. I think it's named as Introduction to Photonics. It covers many aspects of the, let's say, the classical optics and the classical optics as well as the quantum optics, which right now you have not studied about. The quantum optics may be the final portion of this particular course. And yeah, these are the prerequisites. Introduction to Photonics is the prerequisite. The elementary quantum mechanics and semiconductor device physics, definitely you should be knowing in order to proceed with this particular course. So we are into week 5 as per our ritual. So as per our ritual, what we are going to follow is that we have 2 hours in this particular session. So we try to, let's say, take 1 hour for brushing up the concepts which professor has discussed in the week, brushing up the concepts which professor has discussed in this particular week. I guess there are maybe 5 lectures. So this is L1 to L5. So there are 5 lectures in this week, and then for the next 1 hour, we try to solve the weekly problems. Okay, so that is the exact scenario that we try to follow in each of the sessions. So now let's say for example, let's get started. Let's say for example we talk about in the previous lecture we talked about a dielectric nanoparticle. Let's say we talked about a dielectric nanoparticle in presence of an electric field. Let's say for example you have a nanoparticle and you have an electromagnetic wave coming in with certain k vector and certain electric field amplitude. then what's going to happen is that there will be some polarized charge over this, let's say, metallic nanoparticle or a dielectric nanoparticle. I'll tell you, let's say, for example, right now this is a metallic nanoparticle, and here you have a dielectric nanoparticle. Dielectric nanoparticle. So what's going to basically happen is that, let's say, for example, you have a dielectric nanoparticle on this side. Similarly, an electromagnetic wave comes in with certain k vector and electric field amplitude. Then here in the metal, you know that the sigma polarized, which is basically the polarized charge, is given by 3 epsilon naught, epsilon 1 minus epsilon 2 divided by epsilon 1 plus 2 epsilon 2, where this is epsilon 1 and outside index is epsilon 2 into cos theta. That means at the poles, this charge will be around approximately tending to zero, and it will be maximum here. That means, let's say the induced charge will be something like this. Let's say, for example. Okay, and you know that epsilon 1 is equivalent to epsilon infinity minus the plasma frequency square divided by omega square for the metallic system as per the Lorentz model. Okay, but what is going to happen basically is for the dielectric. Here, in case of a metallic system, electric field inside is zero. Inside the electric field is zero. That is the property of the metallic system. You have been talking about it from the class 10 or 10 plus 1 or 10 plus 2 level when talking about the properties of the metals. And for the dielectric, there is some residual field inside. That means there will be some inbuilt polarization. Let's say this is negative, this is positive. There will be some inbuilt field. Okay, so that is particularly explained by something called as me resonance theory. Resonance theory. And I don't think we are going to go into that theory, but if you are interested, you can just look for it. So you have a smaller, one more difference. One more difference is that you have a smaller sigma, which is basically the induced charge compared to that of metal in case of dielectric. And another difference is that there is no phase shift as in case of metal. Remember, you saw in case of a metal when, for example, if this is the electric field, varying electric field, sinusoidal, this is positive and this is negative, positive, negative. So this is the electric field. You remember how the charges looked like if this is the nanoparticle, then you know that this was something like positive, negative, positive, negative, and this is negative, this is positive. That means this was completely out of phase. Let's say, for example, this was completely out of phase with that of this particular, let me draw it like this. This was completely out of phase with respect to the incoming electromagnetic wave. But this phase shift is absent in case of a dielectric. Okay, there is no phase shift between this induced charges with respect to the incoming electromagnetic wave. For example, this is electromagnetic wave, then induced charges will also be in that particular direction. That means if this is positive, this is negative, positive, negative, then induced charges will be something like positive, negative, negative, something like negative, positive, positive, negative, so on and so forth. And it's going to flip over because of the varying nature of the electromagnetic wave. So that is the fundamental difference. And there are definitely a lot of other differences. In case of the dielectric, you talk about something, the dielectric displacement vector, the electric displacement vector, the electric displacement vector is basically epsilon times E plus this polarization. And this is basically electrical susceptibility times the electric field. So this comes into the picture in case of the dielectric. Okay, so and for example, now what we see again is that as per this, for example, as per this me resonance theory, which we are not going to see in the details, but we have seen a glimpse of this me resonance theory in case of let's say if you remember the shift due to the change in the size of a nanoparticle, we saw that there is a shift in the wavelength, a red shift. This is wavelength, and then there was a red shift in case of the change in the size of the nanoparticle. Let's say this is D1, this is D2, this is D3, and this could be explained using simple Lorentz model, using the, let's say, for example, a spring mass system, where you have some positive charge, you have some negative charge connected by the springs, and you have the different spring constants. And as a result, if you have different spring constants, your resonance frequency is going to be different. And you saw that there is a shift, a red shift in the frequency of in this particular scenario. Now, for example, if we talk about the this as per this for example as per this mean resonance theory, what basically happens is that there is something called as efficiency, which is actually the ratio of scattering cross section divided by the area. That means the efficiency is equivalent to scattering cross section divided by the area, pi r square of the nanoparticle. And there are different, let's say, for example, efficiencies. There can be scattering efficiency, there can be absorbing efficiency, there can be maybe transmitting efficiency. Okay, so these efficiencies have different numbers, and it denotes that how much efficient is a nanoparticle in absorbing it or transmitting it. Okay, and let's say, for example, now what we are going to do is that we are going to study the stacked layers and the basically the interaction of the electromagnetic waves and interaction of electromagnetic EM waves with stacks. So that's what we are going to look into. That means if you have, let's say, a periodic structure just like this is where this is refractive index N1, N2, N1, N2, so on and so forth. That means if you have incoming electromagnetic wave, some part of it is going to get reflected, other is going to get transmitted. And what does it depend whether it is going to get reflected or transmitted? And it depends upon a lot of other factors. Let's say, for example, this is this the refractive index periodicity is denoted like this. For example, like this. Let's say N1 refractive index is greater than N2, so you can represent this as a periodic structure where the periodicity is D. Okay, now this D is going to be really important in case of these particular stacks. Why? Because it is this D that basically determines whether a system is going to behave, whether you're going to apply a traditional ray optics or whether you have to go for the full wave simulations or whether you have to use some other kind of approach in order to understand what is going to happen to this incoming electromagnetic wave. Okay, so this dimension is really important, but it is important with respect to what? So if for example this d is much greater than lambda, which is the wavelength of the light, then you are pretty much going to use the traditional ray optics to in order to analyze the for example, what is going to happen. If, for example, if, for example, the incoming electromagnetic wave is 400 nanometers and you have the periodicity of the order of, let's say, 2 micrometers, which is much greater than 400 nanometers, then you're pretty much going to use your simple ray optics, just like you do in your 10 plus 2 level, where you use the Snell's law and other things, and you consider the electromagnetic waves as just rays using the just arrows. Okay, so that is the approach mostly we have been following. But what happens if, let's say, the d becomes approximately equivalent to the wavelength of the light? And in that case, you have to do something called as full wave simulation. You have to go for the full wave simulation where you have to solve the Maxwell's equation self-consistently. And you have to use something called as Maxwell solvers. So you need to solve the Maxwell's equation, all four Maxwell's equation, or whatever you are looking for. You need to compute the electric and magnetic field distributions in case of these systems. But what happens if d goes less than lambda? Now this scenario is important. In this case, you use something called as effective medium trick. Effective medium. Okay. So what you basically do is that if you have a stack, you consider it to be a single medium of thickness T, a single effective medium, but it is anisotropic effective medium. So that is basically what you do. That means it is going to have a effective permittivity in perpendicular direction and effective permittivity in parallel direction. Okay, so let's say this is the perpendicular direction and this is the parallel direction. Okay, so you need to invoke something called as tensors and other things, because now if you write electric displacement field, that is basically epsilon times the electric field plus polarization, then this permittivity is no longer going to be it's no longer going to be a scalar, it's going to be a tensor quantity. Okay, so once you have a tensor quantity, it is something like epsilon It's something like epsilon xx, epsilon yy, epsilon zz, epsilon xy, epsilon xz, so on and so forth. You can fill these columns, and accordingly, you will have the electric displacement vector along x, along y, along z, electric field along ex, ey, ez. So you need to solve this using the tensor notations. Now that is as simple as that. It is exactly what happens basically if you talk about Hooke's law. If you talk about Hooke's law, where let's say for example the relation between stress and strain in a material, and what is going to happen is that you have some stress which is basically equivalent to some, let's say, Young's modulus times the strain. So that is what you write in a simplistic fashion. But in an actual system, this basically modulus is a tensor. So you write sigma to be equivalent to C times the strain, where this is something called as constitutive relations, and this C is basically a tensor. So you have something like C11, C22, C33, C44, depending upon what system you are talking about. Similarly, you can find the other elements. Similarly, you have this stress along X, stress along Y, stress along Z, and you can find and you can do the tensor mathematics, something called as Einstein notation. Einstein notation. That is what basically Einstein used in most of its field equations. So wherever you see the field equations of the in the Einstein's relativistic scenario, those are mostly written in tensor notations because that is taking into consideration the three-dimensional space-time x, y, z, and there is one more time coordinate which is basically t time coordinate. So that in there he talks about the four-dimensional space-time. So that's why the tensor notation also comes into picture there. And tensor notation is it's the actual way to do the physics in order to understand what is basically happening inside the mediums. Okay, so now what basically happens is that if, for example, we talk about now I talked about this particular thing. Now, what we are going to see is that we are going to see how we approach, let's say, for example, uh, in case of a semiconductor, what we do. If you remember, in case of a semiconductor, you know that how do you I have been talking about this in the first lecture even. I talk about how you arrive at the band structure of electrons. Basically, it's a dispersion of the electrons. It's the dispersion figure of electrons. That means E versus K for the electrons, where this K is the wave vector of electron. Okay, it looks something like this. If you draw it in the first Brillouin zone, it looks something like this. Okay, it looks something like this, where you call this as the top of this as the valence band and bottom of this as the conduction band. Okay, and these are this is basically the band gap in case of the electronic structure. This is also the band gap. So why does this arise? Because you have the periodic arrangement of atoms, and then you have basically the electrostatic potential energy because of nucleus. Because of these atoms. So electron feels this electrostatic potential energy, which is, let's say, U of R to be equivalent to some minus K Q1 Q2 divided by let's say for example R. If you talk about the force, then it will be R square. Okay. So if you talk about the potential, it will be R. So K is 1 over 4 pi epsilon. Q1 Q2 is the charge of the electron and the charge of the nucleus divided by R. So you have this is basically the potential felt by the electrons. That means it looks something like this, something like this. This is the nuclear potential felt by the electrons in presence of the nucleus. Then what you do is that you you remove these particular things, they get cancelled. These particular things. Okay, you remove these particular things and you get a structure which is basically the how the electron feels in vicinity of the nucleus. This is basically the potential felt by the electron in vicinity of the nucleus. And at the ends of this crystal, this is high. That's why the electron doesn't leave the crystal. So this is high by the at the ends of the crystal. Okay. So now what is going to happen is that you approximate this particular scenario as a triangular wells. So here you have, let's say, you need to take this. You have, let's say, for example, a well like this. Then you have wells, the rectangular potential wells. Okay. And you solve the Schrodinger equation for one of the wells. Use the condition of Bloch's theorem. Bloch's theorem basically says the repetitive arrangement. Uses the concept of periodicity. So once the system is periodic, you can basically solve for the electron's wave function in one. You can know that what is happening to electron in the other rectangular wells, except that there will be a phase factor associated with it. Okay, so that is how you arrive at E versus K relation for the electrons. Now the similarity here is almost quite similar, except that there won't be nuclear potentials in the photonic systems. There will be this, let's say for example, this is the variation of the potentials. Here in the photonics, you have variation in the refractive index. So you have variation in the refractive index. Let's say, for example, you have a material with high index, low index, high index, low index, so on and so forth. You form a repetitive arrangement. Let's say, for example, this is N1, this is N2, N1, N2, so on, and N2 is greater than N1. Then it is going to form a similar repetitive arrangement of the, I should say, what should I say? Similar repetitive arrangement. These are different layers stacked one over the other, but with a different refractive index. And the electromagnetic wave also behaves just like because in here, when you're solving the Schrodinger equation itself is a wave equation. That means you are treating electron as a wave, and that is basically the quantum nature of electron. But for the photon, the wave nature is a classical thing. And when you treat the electromagnetic wave itself as a wave, which is basically a classical thing for the electromagnetic wave, you are able to solve some differential equations that's going to give you the solution, and that's going to give you the solution as how the electric field amplitude will behave in these particular layers. When you solve here the Schrodinger equation, you get the wave function of the electron, or let's say mod psi square, the wave function of the electron, which basically represents the probability distribution of the electrons. Okay, so here you get how the electric field amplitude behaves inside different layers. Let's say, for example, you talk about case one. Briefly, we'll talk about it. Let's say, for example, you have a system where this is, let's say, x equals to 0 point, and this is x equals to a point, and in this direction is x. Let's say you have some material inside it, which is having a refractive index of n2, this is having refractive index n1, and this is having refractive index n3. So you have zone 1, zone 2, zone 3. And if you assume that some electromagnetic wave is coming in, you will get some kind of a reflection. You assume all the electromagnetic waves to be plane waves. Okay, solution of the Maxwell's equation. And that means it is represented by some e to the power omega t minus kx. And let's say this dimension is d, the thickness of this particular refractive index material. Now you solve the what is called as Maxwell's. You basically solve these equations in different layers. Let's say if you solve in this particular layer, if you solve in this particular zone 1, what you're going to get for, let's say, for x less than 0, you're going to get the electric field as, because it's a wave equation, so it's going to have some kind of a solution as e to the power minus I k, let's say for example k1x x plus b e to the power I k1x x. Okay, similarly for let's say for example this zone, you will get electric field to be equivalent to c I to the power minus k2x x plus d e to the power I k2x x. Okay, so this is for x less than d greater than 0. And for this particular region, you are going to similarly get some e to the power I k3x into k3x minus. Why only single component? Because once the electromagnetic wave goes through this, it's going to get transmitted. There is no other thing here to reflect the electromagnetic wave. But inside, the electromagnetic wave can get transmitted or it can get reflected. That's why there are two components. This is basically transmitted one, this is reflected. Similarly, for the zone one, this is transmitted, this is reflected. So we are treating in this direction, we are treating the electromagnetic wave as e I to the power minus k x x. Okay. just the convention. And now what is the fundamental scenario is to determine these, let's say these coefficients A, B, C, D, and E also. So how you are going to determine that is a different story altogether. Let's say, for example, you compute something called as reflection coefficient. Reflection coefficient, you can compute that how much is reflected divided by how much basically, or divided by the total. Let's say, for example, you can write the reflection coefficient as the B over A. Similarly, you can write transmission coefficient as E over A, because A represents how much overall is incoming. So this represents incoming. This E amplitude represents how much overall is outgoing. That's as simple as that. So transmission will be outgoing divided by incoming. Similarly, reflection will be this B represents how much is reflected at the interface of at this particular interface. Okay. For the other interface, that will be a different coefficient. So that represents the reflection and the transmission coefficients. So you need to take ratio for multiple layers. Okay, so similarly, you can let's say, for example, think about this layer. You need to take the ratio for the for their amplitudes of the coefficients. I'm talking about these coefficients. Okay, that is what happens basically is that if you have multiple layers now, multiple layers, you have to do this task every time at each of the interfaces. And let's say if you have some 50 layers, then it becomes very tedious task. Tedious task. So you want to simplify it and you want to speed it up so that you can solve it and you can do it in a efficient manner, or it should be computationally efficient also, and you should get the solution very quickly. So in order to solve that problem, basically what we shift to is something called as transfer matrix approach. I'm not going to derive it because professor has done a good job in order to make you understand how this transfer matrix can be derived. But the idea is simple. That is the similar analogy we take. Let's say, for example, we have let's say x in this direction, and this is x equals to 0. This is x equals to d. So you have, let's say, zone 2, zone 1, zone 3. This is having refractive index n2, n1, n3. Then what is going to happen? There will be some incoming wave, there will be some outgoing wave. So let's say, for example, the coefficients of their amplitude is A1. For this, it is B1. Similarly, here there will be some incoming waves, and there will be some outgoing waves. Let's say the amplitude is A2 dash. Their amplitude here is, let's say, for example, B2 dash. Similarly, here there will be incoming. Let's say, for example, the amplitude is A2. So outgoing, let's say, for example, amplitude is B2. Similarly, there will be outgoing for the N3, or incoming for the N3, it will be A3 dash, and for this it will be B3 dash. Similarly, you can just have a different coefficients that we obviously know. So now what we are going to do is that we relate these coefficients with the, let's say, for example, you can write the electric field as, let's say, some reflection coefficient e to the power minus ikx plus some L e to the power ikx. Okay, let's say if you denote this as a of x and if you denote this as b of x, what's basically going to happen? You can write the coefficients, let's say, for example, a at if you talk about this interface only. Okay, let's say this interface we're talking about, the pink one. At this interface, the a at x equals to 0 minus, we're talking on the left hand side. That will be equivalent to a1. Similarly, b at x equals to 0 minus is equivalent to b1. And on the right hand side, this side, we can write a at x equals to 0 plus. Just right on the right hand side of this pink interface. You can write this as amplitude as a2 dash. Similarly, you can write as b x equals to 0 plus as b2 dash. Okay. Similarly, you can do at this particular interface, you can write a at d minus is equivalent to, let's say, a2. Similarly, let's say b at d minus equals to b2, and a at d plus is equivalent to a3 dash, and b at d plus is equivalent to b3 dash. Once you write this, now you can relate a1 b1 and a2 dash b2 dash. You can relate these two quantities. That means you can relate this particular quantity with this quantity and this particular quantity with this quantity. And you can do it back and forth, and you can do it continuously. And once you know these coefficients, you can get the what is basically the overall reflection and the transmission. So how we do it? So if you relate the coefficients, you get A1 B1 to be equivalent to A2 dash B2 dash some D1 inverse D2 inverse. With these are the 2 cross 2 matrix. Okay, and you can in general write this as some d alpha, where this can be written as 1 let's say n alpha cos theta alpha minus n alpha cos theta alpha. Okay, and this is for, let's say, for example, if you have a TE mode or something called as S polarized wave. If you have a P polarized wave, or something called as TM mode, then this the alpha matrix, D alpha matrix becomes something like cos theta alpha 1 minus 1. So this is the exact scenario. Now I don't want to go into the derivation of it. You can just follow any of the textbooks in order to understand. So now you only have to understand and get these particular D matrix. Okay. Once you get it, there is one more thing called as P propagation matrix. If you have the knowledge of D matrix and the propagation matrix, you can pretty much know all of these A1, A1, B1, and A2. What are the incoming electromagnetic waves and what are the outgoing electromagnetic wave amplitudes? Okay, and these basically these particular quantities, which are theta alpha, let's say this theta alpha, it can be found out by just simple Snell's law. Okay, and this was outside of it. Now, if we talk about inside the slab, inside the slab, that means we are talking about region 2, inside region 2. What is basically going to happen is that A2 dash B2 dash can be related to P2, which is propagation matrix, times A2 B2. This was region 2. This is region 2. And if you remember, this was, let's say, for example, yeah, this was A2 dash, this was B2 dash, and this was A2, this was B2. So what we are writing is that A2, this particular part is related to this particular part, but with certain matrix associated with it, which is basically the propagation matrix. Okay. And this propagation matrix is, you can write it in general as e to the power I k alpha d 0 0 e to the power minus I k alpha d. That means it is almost like uh, basically the wave is going like this. It can also have a reflected component, so that is why this propagation matrix looks like something like this. Okay. Now, what is going to happen is that this is particularly basically denoting that there is some certain phase vector associated with it. The wave cannot just go from this end to this end and come back here. It is having certain phase vector associated with it. It's almost just like an electron. This phase vector also comes in electrons from the periodicity. And this d is here the thickness of the slab. Okay. Now, what is basically going to happen is that let's say, for example, you have a layered structure with refractive index n1, n2, n3, and you want to have a matrix which is a1, b1, the amplitude of the incoming wave and the reflected wave. Let's say this is a1, this is b1, and this is a2 dash, and maybe let me write it like this. For example, this is a1, b1, and how do we denote it? Yeah, you have something like a2 dash b2 dash. You can write it by writing d1 inverse d2 inverse a2 dash b2 dash. Okay, now here you have written the a2 dash b2 dash inside the slab. Okay, this part is basically inside the slab, inside this particular slab. Now I'm talking about, you can replace it with the propagation matrix. You can write it as d1 inverse, d2 inverse. Now this is propagation matrix, let's say P2, and you can write A2, B2. So now what you have done, you have A2 here, B2 here. Now you have somehow related these incoming amplitudes with the amplitudes at this particular position. That is the essence of it. And now you can go on. Okay, let's say for example, you can now relate this particular A to B2. You can relate it to, similarly, you can relate it to A3 dash, B3 dash using the same logic that we did here. Instead of taking the zone 2, you do it for the, let's say, zone 3, and you solve it again just like this. You will be having a another let's say D2 inverse, D3 inverse. So once you do this, you will get D1 inverse, D2, P2, which is the propagation matrix of 2, and let's say here the scenario is actually yeah, it's fine. So P2, D2 inverse, D3, A3 dash, B3 dash. So now you have this thing instead of this particular. P2 remains same, and these also remain same. Now you go so on and so forth depending upon how many layers you have. So you see a pattern. You see a pattern like you have D2 P2. You have similarly, if you go on increasing the number of layers, you will be having D3 P3, and this goes on and on. So this is a matrix, and this is something called as transfer matrix. Transfer matrix, and it's a very computationally good way to understand what is happening to the waves in these layered structures. Now, in general, you can write, for example, for many layers, for n number of layers, let's say, for example, this is n0, n1, so on and so forth to up to nn, and let's say this is ns. You can write this transfer matrix as a0, b0 is equivalent to d0 inverse, d1, p1, d1 inverse, d2, p2, d3 inverse, d4, p4, so on and so forth, p3, d, let's say, yeah, and it goes on and on to dn, pn, dn inverse, ds. So you see there's a pattern. You have a d1, p1, d2, p2, d4, p4. I think this should be d3, p3. This should be d3. Yeah, that's all. I have a messed up. This is d0, d1, p1. This is d, d2, p2, D3, D3, P3, yes, D3 inverse. This is D2 inverse. Then this is basically D3, P3, and so on. So you see these components here, similarly to DNPN, and so on and so forth, up to the AS dash, BS dash, where this is the AS dash, and this is the BS dash. Okay, obviously, if there is nothing coming back, then this BS dash component will be equivalent to zero. But that is basically how you solve it. So there's a trend. That means this trend can be written as, let's say, D0 inverse, the continuous product of D alpha, P alpha, D alpha inverse, and this alpha goes from 1 to n, and you have ds, as dash, bs dash. So this is as simple as that. Now, how do you write it? You write it in form of matrix as M11, M12, M1, M21, M22. So each of this is a matrix term. And this transfer matrix relates fields from going from left to right. That means it relates the electromagnetic fields here with that of electromagnetic fields going out, and it can also relate it to electromagnetic fields going here, coming back, going here, coming back. You just have to know these matrices, the elements of this particular transfer matrix. So now let's say, for example, you have to compute the reflection coefficient. Then the reflection coefficient can be computed as, let's say, for example, B0 by A0. That can be written as M21 over M11. Similarly, you can write the transmission coefficient as AS dash over A0, which can be written as 1 over M11. Okay, but if you want to take let's say the field magnitude of the reflection coefficient, that is R, that is magnitude of R square, you can write it as the magnitude of M21, M11 square. Similarly, for the transmission, you can write it as, basically there is some factor which comes, which is this particular factor, and you have 1 over M11 square. We'll talk about why this factor comes out. in the later part of this series. So that is basically the scenario. Now, why is it important? Now, for example, you can have a structure and you're going to determine what are the field components, whether it's reflected, whether it's transmitted. Okay, and you can basically design certain layers wherein you can design how the reflection coefficient will behave, how the transmission coefficient will behave. Let's say, for example, there is something called as if this is a slab and you have certain layers in between the slab of varying refractive index. Then if you have an unpolarized light coming in, let's say for example unpolarized light coming in, because of these these particular arrangement of the slabs, okay, one part of it is going to get reflected, the other part of it is going to get transmitted. So, but this reflection and transmission is basically different. The how it is different, that the reflected part is basically the TE part, the transmitted part becomes the TM part. Okay, so it's almost like a this is something called as polarizer, but it can also be called as something called as polarized beam splitter, because it has splitted this incoming beam into two parts. One is the transverse part, another is the transverse magnetic part. And let's say, for example, the 100% power was coming in, then 50% power goes here, 50% power can go here. It depends upon, you can tune this ratio. So this can be like 50-50 beam splitter, but it's a polarizing beam splitter. It is basically dividing the polarizations of the unpolarized light. Okay, and even the polarizers will work on the similar fact. The polarizer does the same thing. It basically so it is sending the S wave on this side and it's sending the P wave over this side. So these equipments are very useful in, let's say, imaging, and let's say for example certain interferometers, and you know these interferometers are the sensitive devices that can measure the displacement, of I should say the minute displacements. One of such interferometer is basically used in something called as LIGO, light interferometry gravitational observatory, which is basically a interferometer where the two beams are getting interfered, and because of the path length difference, the gravitational waves are detected. And there, these equipments are really necessary. They use, let's say, for example, some kind of a vacuum system, but the interferometer configuration remains the same. Okay, so these are going to be essential for all of the physics applications. They are all correlated. Now, what we are going to talk about is a photonic band gap. The photonic band gap arises now, for example, what is the concept of a photonic band gap? Photonic band gap. Photonic band gap is just like, for example, if you have some reflectivity, if you have reflectivity versus the wavelength curve, and it looks something like this, then basically what is happening is that this part of the electromagnetic wave or the light is getting reflected from the system. That means it's not accepted by the system. That means the rejected part. And that basically denotes the gap. Band gap indicates that these wavelengths of the electromagnetic waves are not accepted by the system. They cannot propagate in the system. So they get reflected. For example, if you have a certain slab, if you shine some electromagnetic wave where the electromagnetic wave wavelength, let's say, lies between A and B point, okay, so that is going to get reflected. That's not going to get transmitted or accepted by the system because of this particular gap. It's just like electronic band gap. Similarly, if you have, let's say, for example, you have a crystal, and if you have electrons moving through the crystal as block waves, then you know that because of I should say the way you solve it, the periodicity and multiple waves interfering with each other. Okay, That interference basically results in destructive interference somewhere and constructive interference somewhere, and that results in basically the band gaps. This is the electronic band gaps. So that there we talk about these electronic band gaps. That means electron cannot have these energy values inside the lattice. As simple as that. Similarly, the photonic band gap is like the photons cannot those particular wavelength of photons, these particular wavelength of the photons cannot flow through this particular system. So that is the simplest idea of a photonic band gap. Okay, so now what does it depend upon? Let's say, for example, if you are what's called as the the dimensions become of the order of wavelength. If your d becomes of the order of wavelength, that means the let's say for example you have a stack which is having certain repetitive arrangement d, and if that becomes of the order of wavelength, then this photonic band gap becomes necessary, comes into picture. You need to consider this effect. That means now there will be certain wavelengths of the light that will be rejected, that won't be accepted by the system. Okay, now what is going to happen is that, let's say for example you have a lattice. For example, let's say for example you have a repetitive arrangement of the lattice. When I'm talking about repetitive arrangement, I'm saying that this is, let's say for example, is having a refractory index n1, this is n2, n1, n2, so on and so forth. Okay, then you can have, let's say for example the periodicity of this particular thing is, let's say for example this particular periodicity is a, and what you can have is that you can have the wavelengths of the multiples of a. Let's say so you can have somewhere the wavelength which can fit into two slabs. That means the overall wavelength can be 2a. But somewhere you can have the wavelength which can fit in a single slab. That means the wavelength is going to be here the wavelength is going to be a. Okay, and what does it depend upon? It depends upon what is the dimension of this particular system. That's why I talked about these gaps come into picture when d becomes of the order of wavelength. You see that whenever this particular thing becomes of the order of wavelength, then basically the electric field is flowing inside these particular structures, and this represents the spatial, I should say, distribution of the electric field. So it's like E as a function of X, electric field as a function of X, and this is X, and these are spatially behaving just like this inside these particular lattice. Somewhat like the electric field amplitude will be maximum here, it will be minimum at this particular point. So almost like a wave inside it. So now what is going to happen is that you can have a, because of these waves flowing inside this particular system, you can similarly have a dispersion diagram for the photons. But obviously these are we're talking about photons, so the dispersion will be flat. We are talking about electromagnetic waves, okay, and then you will have in the reduced zone representation, this looks something like this, okay. But once the gap opens, because of the reason I told you, then it's going to look something like this. So there will be these gaps opening. Okay, one of the reason is also because, let's say for example you have atoms. So because of this arrangement of atoms, when the electron, if you let's say have some electron waves shining at this particular structure, you will see that because of these are because these are waves, and because of the interference of the waves, just like the constructive and destructive interference, there will be certain regions or certain energy values which are accepted and certain energy values which are not accepted. With the values which are not accepted, that means they undergo destructive interference. That gives rise to a band gap. Okay, this constructive interference gives rise to a allowed values of the energies. That is as simple as that. You can make an analogy. because these are all waves flowing inside this particular system. Similarly, the for the electromagnetic waves, these are basically the waves flowing inside this particular stack. And once they hit, let's say for example, some wave comes in and it hits this stack, it undergoes reflection. Then some part goes here, that it undergoes reflection. Some part goes here, undergoes reflection. There's back and forth reflections, and that creates constructive and destructive interference. And now we cannot track it all through the structure. So that happens, it happens so that now because of those constructive and destructive interferences, there opens a gap just like this, just like these gaps. So these photons can create destructive interference and they can no longer be sustained in this particular stack. So they open a gap which is basically called as photonic band gap. Photonic band gap. Okay, and just like I told you, how does this wave behave in the lattice? It can behave in a different way. It depends upon the wavelength, how much is the wavelength with respect to the periodicity of this particular system. Okay. Now there is something called as permittivity contrast. Let's say, for example, when I talked about these stacks, I talked about, let's say this is the different stack. Let's say, for example, this is gallium arsenide. This is gallium aluminum arsenide. Similarly, this is gallium arsenide, so on and so forth. So this is having refractive index N1, N2, N1, so on and so forth. That means the the permittivity, electrical permittivity is epsilon 1. Here it's epsilon 2, epsilon 1, epsilon 2, so on and so forth. And you know that n is equivalent to under root mu times epsilon. Let's take mu to be equivalent to 1 for a time being. We are not considering the magnetic material. We are considering mu to be 1. So n will be equivalent to under root of epsilon. But you know that this epsilon is actually imaginary. So you have actually, this is also imaginary. So you can write it as just like this. You can write n1 plus I times n2 is equivalent to under root of epsilon 1 plus I times epsilon 2. Okay, solving this, what you get is basically, let's say you get epsilon 1 to be equivalent to n1 minus n2, n1 square minus n2 square, and epsilon 2 to be equivalent to twice n1, n2. That's why when you solve it, you just square on the both sides, and then you compare the imaginary and the real parts. So that is what we have been telling you, and this imaginary part basically represents the losses in the system, the absorption in the system, the absorption of electromagnetic wave. Now, what is going to happen? Let's say, because this structure, it is quite I should say sometimes counterintuitive to understand it, because this structure is also similar in, if you something called as, if you call this as something like superlattice structure. Those of you who are from device physics, they also know this, that this is a superlattice structure. That means you are having, let's say, a quantum wells, which are the repetitive arrangement of the quantum wells. Okay, and you have certain energy levels in these quantum wells. And the wave function in these energy wells for the electrons I'm talking about looks like something like this in energy E equals to 1. So let's say this is the conduction band, and similarly you can draw the valence band. This I am right now drawing the, this is the electronic band diagram. And this EC and EV basically represents the, let's say for example, this is EC for material 1, this is for EC for material 2. Similarly, this is for EV for material 1, this is EV for material 2. This one. Okay, this is EC. Now, what is basically going to happen? These are basically potentials. These are the variation in the potentials, electrostatic potentials for the electrons. Now, because of different layers, because let's say for example this is layer 1, this is layer 2, similarly this is 1, 2, so on and so forth. Now you see that the band gaps are also different. Obviously this band gap is larger, this one is smaller, this one is larger. So let's say Eg1 is greater than Eg2, and it goes so on and on. And also, you know that the refractive index is dependent upon the band gap. Okay, obviously. I mean, it is a band gap dependent thing. That is why certain electromagnetic waves are absorbed inside the semiconductor. Let's say you have a semiconductor of energy gap of 1.2 electron volt. So if you have an incoming a photon of 1.2 electron volt, it will get absorbed and will create an electron hole pair in the system. And that is governed by this Eg. And Eg in turn controls the refractive index. So they have an inverse relation. If you see that how the refractive index behaves with the Eg, it goes as inverse. That means as the band gap increases, the refractive index reduces. Okay. Now, what does it mean? It means that now you are going to have a different, you're also having a I should say refractive index variation here because of this band gap variation, right? So now whenever the electromagnetic wave, now when we talk about, let's say for example, the refractive index profile will look like something like this. Just like I said, the variance inversely. This is the refractive index profile. You don't need to show the valence or conduction band here because it's just like the variation of refractor. It's just like this is N1, this is N2, this is N1, so on and so forth. So now what happens? Now when an electromagnetic wave comes, it's going to face this periodicity. One, because there is a different band gaps, another there is a different refractive index. So what is it going to select? I mean, what is going to govern whether this electromagnetic wave will get absorbed or whether the periodicity of the refractive index is going to make it reflect or transmit? What is going to be a governing factor? So that is a crucial role. That is why we almost most of the time try to match the electronic energy gap and the photonic energy gap. Okay, let's say for example, I give you an example that let's say for example this particular structure, an electromagnetic wave. Let's say for example in this structure an electromagnetic wave comes in. Let's say electromagnetic wave comes in, and let's say for example this is how much is let's say for example this particular what should I say? Let me just draw. Let me just make you understand from this. Let's say electromagnetic wave comes here. It faces both refractive index gradient, that means this, as well as the potential gradient. Okay, because of the nuclear potentials. Now, when an electromagnetic wave comes in. Let's say this is at let's say it's 800 nanometers. Okay, I just want to give you good numbers. Let's say, for example, this is 1024 nanometer, which is almost like a IR in IR region. And and if the band gap is such that this particular wave is going to get absorbed, then the band gap is going to determine the how the electromagnetic wave will behave. That means this is going to get absorbed. No matter if the refractive index variations was allowing it to get reflected, this will get absorbed because it is going to create electron hole pairs. Okay, and that means the absorption is going to happen. That means if you have a arrangement of conduction band and valence band like this, okay, then this electromagnetic wave is going to come in and it is going to basically get absorbed if it is 1024 nanometer. And if let's say this band gap is of the order of 1024 nanometer, the energy value, then it's going to create the actually I should show it like this. Let's say for example this value is of the order of 1024, then it's going to create an electron hole pair and it's going to get absorbed. Okay, no matter what basically the refractive index gradient is telling it. Because in the refractive index, there is a real part and there is also an imaginary part. And this is also important because this governs the absorption coefficient. That is why most of the time we try to match the electronic, electronic and photonic band gap. Because it does not make sense that you have a, let's say, for example, let's say you have a photonic band gap at, let's say, 1000 nanometers. Let's say, for example, you have a photonic band gap at 1000 nanometers, but an electronic band gap is going to accept that particular value. Let's say, for example, let's say 1000 nanometers correspond to 1 electron volt. Let's say, I'm saying it, example. And let's say, for example, this electronic gap was one electron volt. Then obviously this is going to get absorbed and electron hole pairs are going to get generated. That is what basically I mean. So both of these govern the absorption and the transmission of these electromagnetic waves inside the structure. Now we are going to see, let's say for example, there is something called as, if you have the permittivity of this is epsilon 1, epsilon 2, epsilon 1, so on and so forth, there is something called as permittivity contrast. So how much is the variation in the permittivity, and it's given by delta omega over omega, which is delta epsilon by epsilon sine of pi d divided by pi. I guess this is a pi d over a. So this basically also tells us what is the frequency. This is basically the normalized frequency, which is on the y-axis of this of the dispersion plot. So it's going to tell you what are the accepted values of the frequencies depending upon what is the contrast, what is the variation in the refractive index, which is the delta epsilon is basically epsilon 2 minus epsilon 1 or epsilon 1 minus epsilon 2. Okay, similarly, you can write the values. And delta omega by omega is basically it represents something like a called as band gap divided by mid gap value. It's a ratio of these two quantities. Okay. Now, what else is there? Let me just think about it. Introducing. Okay, similarly, if you have, let's say, for example, you can induce a, you can have a defect in the photonic, defect in stack. Let's say, for example, your periodicity breaks. You had a refractive index gradients periodicity like this, but somehow you have a different layer in between where there's a, this is basically like acts like a defect. Just like if you have atoms, but if there is some, let's say, for example, defect or some different atom placed here, then this nuclear potential will look like something like this. But at this particular position, nuclear potential will get perturbed, and you will have a different potential here that is going to perturb the wells. I don't know how it's going to look like here, but that's going to disturb it. So that behaves like a defect. Similarly, this behaves as a defect, like here, it breaks the periodicity. Okay, now it's not no longer periodic at this particular point. So this gives rise to a photonic band gap. So then there is a defect in between, and this is again a repetitive photonic band gap. Okay, so now what we are going to see is I guess diffraction grating we will see in the questions. That is quite simple. That's not much involved. Yeah, so let's jump to the questions first of all. We have discussed a lot of things. So there's 1 hour only remaining. So this is the first thing I guess the professor has discussed. These are, and we also discussed it in the last lecture, that these are some scattering efficiencies versus the wavelength for different nanoparticles. Let's say you have a nanoparticle 1, you have a, let's say, nanoparticle 2. There are two nanoparticles of diameter 160 nanometers, and we have to identify the material for these nanoparticles, whether it is a dielectric material or whether it's a metal. So we have to identify that. First of all, the you don't have so many features in case of a metal, just like these features. These are very rich features, which are the properties of dielectric. The metals don't have such rich features in the case in the scattering versus the wavelength plot and the resonance plots. Okay, so that is one of the hints, but that's not enough to understand it. The important thing is that there is electric dipoles, and this is basically electric dipole, this is magnetic dipole, this is electric quadrupole, magnetic quadrupole, electric octopole, magnetic octopole. So in case of metals, in case of, let's say, for example, this particular system, you have the magnetic dipoles, but here you don't have the magnetic dipoles. Similarly, here you have the magnetic octopole, but here magnetic octopole scattering efficiency is zero. And this is basically the property of the metal. Why? Because you have talked about that talked about something called as the what basically this magnetic resonance depends upon. It depends upon the induced circulating currents that couple to the magnetic component of the light. Okay, and what is going to happen is that optical frequencies, what we are mostly dealing with at optical frequencies, the I should say, in case of a metals, they are having very high plasma frequency. Okay, and mostly we talk about the magnetic permeability to be almost equivalent to one. If it's not magnetic material, okay, we're talking about a metal, then the magnetic response is going to be negligible. First of all, that is a one vague argument. Then the magnetic response is going to be negligible. Okay, that means you cannot get a resonance from this magnetic. You cannot have magnetic dipole or monopole in case of this metallic system. But what is basically going to happen? It can support the electric resonances, just like you talked about surface plasmon resonances, LSPRs. That those are basically electrical resonances in the metals. But for the magnetic resonances to occur, it would require the induced circulating currents that can couple. Let's say this is a nanoparticle, then there should be some induced circulating currents that can couple to the magnetic component of the magnetic field of the magnetic field of the electromagnetic wave. So that doesn't happen. Okay, because the incident light's magnetic field is too weak to induce significant circulating currents, and the incident, I should say, what should I say? The optical frequencies we are mostly concerned with, at those frequencies it doesn't happen. But sometimes people are working on it, and it can happen at some other frequency. So that's why these rich features, first of all, are the features of the dielectric, and you don't get these magnetic monopoles and magnetic octopole, sorry, not a monopole, and the magnetic dipoles in case of a metallic system. Okay, so that's one of the thing. What else can we see? So that means this A is going to be dielectric, this B is going to be uh, metallic. So this is the answer of this question. So just we have to justify our answer is that the A is a contribution from electric and magnetic poles, but B has a contribution of electric poles only. That is why the magnetic monopoles or so not the monopoles. Why I'm saying monopoles? Magnetic monopole does not exist, at least till now. What we have been talked about. So these magnetic dipoles and the quadrupoles, they do not exist in the metallic system. Okay, so what else? So a graduate student now is another question where it has been said that the graduate student computes electric field distribution of the electric dipole and the magnetic dipole mode in a gallium arsenide nanoparticle. You see that there is a magnetic dipole mode. That means it's a gallium arsenide. That means it's a dielectric material, and it's of the diameter of 200 nanometers. He or she understands that E field has enhanced at mere resonances. Now he comes to you for asking the guidance on which to use for sensing and which for lasing applications. Suggest your answers. Okay, so there are two nanoparticles. Let's say this one electromagnetic wave has come in, and you get a This color is basically showing the response of the electric field strength. The electric field strength is more here, but for this nanoparticle, the B nanoparticle, the response of the electric field strength is more at this particular position. You see that this is dielectric, otherwise the electric field lines would not exist inside. Okay, if it was a metal, then electric field inside is zero. But this is dielectric, that's why the electric field, this strength is basically shown inside. This bar basically shows the electric field strength, electric field distribution or the strength, intensity. What's going to happen? Now, what are we going to use for what purpose? Now, there are two things. He wants to use for one for sensing and other for lasing applications. Well, we have sensing, we have lasing. For the sensing, you want something, let's say you want to sense some particles. Then you want those particles to get applied on this nanoparticle. Okay, that's obvious. You want those particles to touch the nanoparticle. And once it touches the nanoparticle, then it should change the distribution, change the electric distribution or magnetic electric dipole or magnetic dipole distribution. So the efficient way to do is that if the phenomena is happening over the surface, or if the electric field strength is maximum at these particular regions, the those particles or the molecules, whatever you want to sense, they are going to change this particular distribution, and because of that change, you are going to sense it. So this one sounds a good choice for the sensing application because it has a maximum electric field intensity, dipole intensity outside this particular nanoparticle. Now for this one, it has a component inside. Maximum component is present inside. If you draw this, it is something like this. This is the electric field distribution. It is maximum inside. Okay. And then it's leaking out from this nanoparticle. It will be better for something like light guiding because it's almost like inside the nanoparticle. I'm not telling you it can be used for guiding, but because of the confinement, the electric field is confined inside the nanoparticle. That is why it can be used for certain light applications, just like, for example, lasers, lasing. In the lasing application, you want the most of the electric field distribution to be present inside this particular system. Okay, so let's say, for example, let me talk about even if you have, let's say, how does a laser work? You have some active medium, and you have, let's say, for example, some reflectors. So this is called as cavity. So you have a photons going back and forth in this cavity. They interact with the active medium and they emit a coherent source of the electromagnetic waves. And that basically by the process of something called as stimulated emission. There is something which is pumping this active medium, giving it energy so that the stimulated emission can happen. So stimulated emission is like you have the electrons here, so all of the electron come down suddenly, simultaneously, and emit a photons which are coherent. So those waves are coherent in nature. Okay, so that gives rise to lasing. Now, if you want to make let's say, a laser, let's say based on semiconductors, then you want the confinement of the electromagnetic field. Then it's going to produce certain guiding of the electromagnetic wave. Okay, then that's only possible if the distribution is, let's say, for example, something looks like this. That's as simple as that. So A is suitable for sensing and okay, it's a different answer. A is suitable for sensing and lasing when gain medium is in the vicinity, but outside the nanoparticle. Yeah, that makes sense. And B is suitable for lasing when the gain medium is nanoparticle itself. Yeah, that is what I talked about. This active medium is basically the gain medium. If the active medium is itself the nanoparticle, then it's going to behave as a lasing system, so that the maximum electric field distribution will be inside. But if the active medium is in the vicinity of the nanoparticle, then the A is also going to give rise to a lasing action. These are two different scenarios. Okay. And with respect to your answer to the above, choose the correct statement from the following. MD mode leads to enhancement of the electric field inside the particle. The ED mode enhances electric field. Yeah, the electric dipole enhances the electric field. The magnetic dipole enhances the electric field inside the particle, and the enhanced exterior electric field is suitable for sensing annihilates. Enhanced electric field leads to efficient light matter interactions. So that's what basically I discussed. So you can perturb the external electric field by using sensing, let's say sensing molecules, and enhanced electric field leads to efficient light matter interaction. Yeah, that is as simple as that. Okay, so where are we? So now for question 5 to 6, what are we going to do? We have to consider a stack of slabs of refractive index N1 and N2. Let's say this is N1, N2, N1, N2, so on and so forth. So this N1 is titanium, N2 is silicon, just like a metal semiconductor stack. And what we are going to do, what is given? We have to compute the angle of refraction at interface 2. At interface 2. Okay, so it's something like you have a, let's say this is air, which is n equals to 1. This is n1, this is n2. So this is interface 1, this is interface 2, this is interface 3. So there are three interfaces. One is air titanium interface. This is titanium, this is silicon. Another is titanium silicon interface, and another is silicon air interface. So we need to compute at this particular interface. Oops. Oh, the color. We need to compute at second interface. What we need to compute the angle of refraction. So how we are going to do it, that means there is some electromagnetic wave that is coming in, it's going to get refracted and it's going to get transmitted, then it's going to get refracted. And if you draw the normal of these, then you have theta 1, you have angle of refraction. Similarly, you have this as let's say theta 3, and similarly you have here as theta 4. And we are going to solve it. You have to compute the refractive index of layer N2. You have to compute the refractive index of this layer. How you do it? Just use the simple Snell's law. You can write n1 sine theta 1 to be equivalent to n1 sine theta 2. Oh, no, just a mistake. This is n. Yeah, this is n, this is n1, this is n2. You can write n sine theta 1 to be equivalent to n1 sine theta 2. Simple as that. Theta 1 is given 20 degrees. So it's given 20 degrees. So you have, and n is 1. So this is 1. So you have sine 20 degrees to be equivalent to n1 is 1.5. It's given sine theta 2. So you can have theta 2 to be equivalent to sine inverse of sine 20 divided by 1.5. So this is around 13 point, I guess 13.2 degrees. So this is theta 2. Now when you have found theta 2, you have to apply the similar logic. You can write at the other interface n1 sine theta 2 is equal to n2 sine theta 3 at the interface second. And you can get n2 from this. You can write n2 as n1 sine theta 2 because theta 2 you have obtained divided by sine theta 3. Where is theta 3? Theta 3 is exactly theta 1. Why? It's almost like vertically opposite angles. So this theta 1 is equivalent to theta 3. Theta 1 is equivalent to theta 3. So you get n2 to be equivalent to 1.5 sine of 13.2 degrees divided by sine of 10 degree. So you get n2 to be 1.9, around 1.97, I guess. Okay, so we were supposed to find this. So n2 is 1.97. So 1.96 is the exact answer. So it's almost like maybe some calculation mistake. I guess this is something like 13 point some 16, something like that. Yeah, so it will be around 1.96. So what should be the value of refractive index such that the angle of refraction at interface is 20 degrees? So it's saying that what should be the value of n2 such that theta 3 is equivalent to 20 degrees. So we need to find n2. Similarly, we can write n2 sine theta 3 to be equivalent to n1 sine theta 2. And n2 sine theta 3 is equivalent to n1 sine theta 2. That means we can write n2 to be equivalent to 1.5 sine of 13.2 degrees divided by sine of 20 degrees. That means n2 should be around, I think you get 1. So n2 will be equivalent to 1. That's it. Now choose the correct matrix expression for evaluating terms of transfer matrix. Yeah, this is the transfer matrix I was talking about. So if you have a stack of layers with, let's say, n0 refractive index, n1, so on and so forth, nn and ns refractive index, let's say this is nn. How you are going to represent, let's say this is an incoming electromagnetic wave, this is reflected, this is transmitted. Okay, so you represent the amplitude as a0, b0 is equivalent to some d0 inverse, the product of d alpha, p alpha, d inverse, ds, as dash, bs dash. So this is the answer of this question. Nope, not this one. Oh, this is the answer of this question. Yeah, that's what I talked about in the upcoming previous slides. How do we arrive at this particular position? That you have to continuously product these particular matrix terms, and you get this terminology of transfer matrix, just knowing the propagation matrix and the D matrix. Now, the question about the photonic band gap. The photonic band gap is a forbidden energy gap in a photonic crystal. I talked about it. Just like in electronic crystal, certain energy values are not accepted in the photonic system, and you get these gaps. So defect states can be introduced in the material to create allowed energy states with the photonic band gap. How do you create the defects? Let's say you have a variation in the refractive index like this. Then you can create defects by, let's say, altogether having a different system material here. So this acts like a defect state, okay, for the photonic crystal. So we have to choose the following statement. So light with the wavelengths lying in the photonic band gap reflects. Yeah, that is exactly correct. So if you have some light incoming, that is almost of the, let's say for example, this is the band gap, photonic band gap from A to B. And if the wavelength is in this range of from A to B, then that particular wavelength is going to get reflected. That's what I talked about. So basically this will give you frequency, so you can convert the frequency to wavelength. So that particular wavelength will not be accepted by the crystal. And that is what the first answer says. The second says light with wavelength lying at photonic bandgap transmits. That's absolutely wrong. The system does not accept those wavelengths. Creating a defect allows designing very narrow band transmissive filters. Creating a defect allows designing very narrow band reflective. Yeah, so if you create a defect, then it will allow you to design a narrow band transmissive filter. That means if you have a transmission coefficient, it can have a narrow band transmission at some particular wavelengths because of those defects. So this is basically a narrow band transmission. So these particular wavelengths of the light will be completely transmitted because of that particular defect. And that is how you fabricate it and how you do the designing of these different stacks. Okay, so I think that has been talked about in the that has been talked about a lot. Now, what else do we have? We have a periodic structure. We have a periodic structure, a periodic diffraction grating. So the diffraction grating is just like if you have some substrate and if you have certain other refractive index materials, let's say this is N1 and these are N2 all, then if you shine some light, then you're going to see that some part of the light is going to get, there'll be diffraction patterns with n equals to 0, n equals to 1, n equals to 2, n equals to minus 1, n equals to minus 2. Just like if you have a prism, you shine some white light. White light basically consists of all colors, so I'd like to show it in all colors. So if you shine these colors to the prism, you are going to get the violet, you'll get indigo, I guess this is indigo, blue, vib, G, green, orange, yellow, similarly, all other colors. You're going to get a dispersion or they are going to get separated based on the wavelengths. So that is the similar phenomena that diffraction grating does. Okay, and it is very useful because it allows us to selectively select certain particular wavelengths. Okay, now what is the question? A periodic diffraction grating is fabricated on glass. Let's say the bottom substrate is 1.5. This is glass with 100 slits. So these slits are like 100 in number. So there are 100 slits, and periodicity is 2 micrometer. That means they are repeating at 2 micrometers. Electromagnetic wave incident on the grating results in second order maxima subtending an angle of 30 degrees. So the second order maxima is like if you have a if you have an aperture of the order of wavelength of the light. Let's say this is D and you have an incoming electromagnetic wave. You know that there will be diffraction pattern forming with the intensity at the maximum. Then there will be like a sinc function. Sinc function. So this is like the first maxima. This is the second maxima. This is the third maxima, so on and so forth. This is the first minima. This is the second minima. Okay. So he's talking about the resulting second order maxima subtends an angle. Second order maxima means n equals 2. Subtends an angle of 30 degrees with respect to the normal. Okay, so that is basically making an angle of 30 degrees with respect to the normal. Let's say for example, this is the incoming wave at a normal incidence. Normal incidence means theta incident is equivalent to 0. Okay, because it's with respect to the normal. So that's it. That means if let's say for example you have this theta is like this. This is theta incident. So if you go in this direction, that will make theta to be equivalent to 0. That is normal incidence. Okay. So it's saying that this is making an angle of around plus minus 30 degree because there will be one here, one going here. So he's saying that it's making an angle of minus 30 degree and let's say plus 30 degree with respect to the normal. N equals to minus 2, n equals to plus 2. So this is the scenario. The second order uh, maximas are subtending an angle. What is the wavelength of the incident wave? So we need to find the incident wave's wavelength. How we can do it? We can just simply use d sine theta equals to n lambda. Where does this come from? It comes in a lot of I should say equations. This is basically a grating equation. You see also this in something like Bragg's diffraction, X-ray diffractions experiments. And this n lambda basically is like an integer multiple of lambda. That means these are going to be if it is a multiple of n lambda, then this indicates like constructive interference. If it's like 2n plus 1 lambda by 2, then it's going to have destructive interference, so on and so forth. I guess you know about it in detail. So we can use this equation. So d is given 2 micrometers and theta is given as 30 degrees and n is given as 2. Lambda is to be computed, but note here that this lambda is basically lambda over n glass because the wavelength is going to change in the glass. So you have 2 into 1 by what is sine 30? It's 1 by 2 equals to 2 into lambda over 1.5. So lambda you get around 0.75 micrometers. So that means the wavelength of the incoming wave based on at what angle the diffraction takes place of the second order intensity, the wavelength would be around 0.75 micrometer. That means it is 750 nanometers. So 750 nanometers is the answer of this question. Angle 30 degrees subtended by two maximas. Okay, that's what I basically. Okay, I don't know what this means. Use momentum conservation across the interface. Yes, that can also be used. I mean, basically, if you have, let's say, for example, you can write a momentum conservation equation also in terms of, let's say, for example, you can have some incoming wave vector k1 sine theta 1 minus k2. This is not momentum conservation exactly, but we can write an equation like this where this g is 2 pi by a. Let me see whether we can do it like this. Hmm. If we have to write the momentum, then we can write as h bar, h bar, h bar. So you can write h bar. Okay, that will be okay. Yes. So that is basically h bar k1 will be the momentum of p1 sine theta. Yeah, then we can resolve it that way also. But this is going to give us the exact answer. Let's forget about this right now. Okay, what else? Are we done? Okay, we are we are into the final question where we have the concept of the configuration of multi-stack. Multi-stack layers means you have a stacking of different layers and consisting of 20 pairs with same periodicity. The layer permittivities are given epsilon h and epsilon L and A for materials A and B. So you have gallium arsenide and material A and gallium arsenide and material B. So the reflectance spectra is shown. For this, you are given that the reflectance bandwidth is larger. For this, the reflectance bandwidth is smaller. That means it's only reflecting these wavelengths, but here it's reflecting a lot more wavelengths. So the photonic band gap here is higher. So the photonic gap is larger, I should say larger for A compared to B. That is one observation we can make. But we need to show what is the permittivity of epsilon LA. The permittivity of, I mean, we need to compare the permittivity of epsilon LA and epsilon LB. That's what we need to compare. So how are we going to do it? So we saw that we can write delta omega by omega as delta epsilon by epsilon, some sine pi d over a divided by pi. So this is basically the permittivity contrast. So if the permittivity contrast is larger, then I should say the reflectance band is going to be larger because this band delta omega by omega normalized frequency is directly proportional to delta epsilon by epsilon. So if this permittivity difference is larger, then this band is going to be wider. Okay, so this is going to be wider. That means for this particular stack, for this particular band, which is narrower reflectance band, it is having greater epsilon. Okay, epsilon LB. So the epsilon LB will be greater than epsilon LA. So that means epsilon LA is smaller than epsilon L. Just comes from the fact of permittivity contrast between the two materials. So it's like you have a gallium arsenide and material A, for example. So for example, you have gallium arsenide and material A, gallium arsenide and material A, so on and so forth. Then you have gallium arsenide and material B, gallium arsenide and material B, so on and so forth. And epsilon H is given as 13, which is basically for the gallium arsenide. These are like 20 pairs with same periodicities, okay? The layer permittivities are epsilon H and epsilon LA and epsilon LB. Okay, this is epsilon LA, this is epsilon LB. So that is exactly what is the scenario. Okay, yeah, so we are done with the today's session. So if you have any questions, you can just post it or you can just mail me, and we will meet in the next week for the week 6, where we're going to see the electromagnetic waves in 2D crystals, electro and magnetic metamaterials, hyperlens, superlenses, negative refractive index, a weird concept. The refractive index becomes negative, but it's not weird because we showed you in a if you have imaginary component of refractive index, permittivity and permeability. Similarly, you have this real part of refractive index epsilon and permeability. Then you can play with this particular thing in the imaginary space. You can have a refractive index imaginary. You can have a refractive index negative. You can have a refractive index positive, which is the usual scenario, so on and so forth. And what is going to happen is you go into different materials, let's say metamaterials, how the light behaves in different materials. So that's what we are going to talk about in the next week. Okay, so then I think we are going to talk about light emitting metamaterials, amplified emissions. Okay, we are going to talk about lasers also. That is also interesting. And then we are going to talk about nanofabrication. This is fabrication related, fabrication of the materials. And from here onwards, you go into the quantum photonics regime. So in the quantum photonics, that is the my favorite part, to be honest. You talked about light not as electromagnetic wave, but as photons. And now the picture completely changed because this is like a quantum entity. It's no longer governed by the classical physics or the Maxwell's equations or the classical rules. Okay, and now then you talk about photon anti-bunching. What is bunched source, anti-bunched source? You talked about this is the core quantum mechanics. You talk about canonical quantization, quantum harmonic oscillators, vacuum fluctuations, or something called as I should say vacuum energy fluctuations or quantum fluctuations. You talked about coherent states, number phase uncertainty. Okay, so that is going to be interesting. Then you will talk about time-dependent Schrodinger equations, strong and weak coupling, Rabi oscillations. Okay, so that beyond week 9, it's going to be more interesting. Okay, for me as well because I like this part very much compared to that of the the classical part. Obviously, but one has to know the classical in order to just jump into the quantum mechanical. You cannot go into quantum mechanics without knowing the classical. Okay, so that is it from my side. I'm going to stop this lecture. See you next week.